Good evening, everyone. Welcome to week 7 of the sessions on regression analysis. Today, we'll be understanding and solving a few problems related to week 7 lectures. So, let's get started. Alright, so during week 7, what did we learn? So, before that, I'll just briefly brush up on what we learned in the previous week. So in week 6 we learned about multicollinearity. So what is multicollinearity? This problem arises when we have multiple regressors which are correlated within themselves. Okay, so one or two regressors are highly linearly dependent. Now if they are perfectly dependent on each other and there exists a perfect linear relationship, then we have seen that we do not get a unique value of the estimate because x transpose x inverse x transpose x doesn't remain invertible at that point. So that's the thing, that's what happens when they are perfectly linearly related. But what happens if they are not perfectly linearly related but there is a high level of linear dependency? Then these are the problems that arise. Okay, we can have large variance and covariance of regressors. The least squares of regression will be very far from the actual true parameter, and then there could be a reversal in the direction of effect. These there could be situations where the global tests is highly significant but individual tests or partial tests are insignificant. Okay, this is one situation that could arise, and we can have a chance of getting different model from different model selection techniques. Okay, so these were the problems what can happen, and we also learned how to detect. So if we have two regressors, we have to find out whether the x transpose x matrix, if the diagonals or off diagonals are showing, if the off diagonals show high values closer to 1, then we can say that okay, maybe these are related linearly, and then we just remove one of them or do something. Or we have also learned how to use the condition number, okay, and also variance inefficient factor. Alright, so these were the ground rules that we usually follow if we detect multicollinearity with the condition number criteria, and this is what we follow with the VIF or variance inflation factor criteria. In order to fit a in order to get VIF, we fit one regressor upon others and then find out the R square value for that equation, and then VIF is 1 by 1 minus R square. Okay, now in the case where we find multicollinearity in the data set, what do? We collect additional data, or we remove 1-2 regressors, or we collapse using principal components. That was all about week 7. Sorry, that was all about week 6. Alright, so in week 7 we learned about model adequacy check-in. What do we mean by model adequacy check-in? So it usually means that validation of assumptions on the errors. So what were the assumptions that we had? We had assumption that expectation of errors were 0, variance of errors is constant. Okay, we had this homoscedasticity assumption, and also for testing we assumed that these follow normal 0 sigma square. Okay, so now we have to, so this week we discuss how to check whether these assumptions on which a linear regression holds. So this week we have to check that the assumptions on which the linear regression is built upon, whether those hold or not. Okay, and in the context of testing out these assumptions, we learned about two very important concepts, which are a leverage point and an influential observation. So I'll just briefly discuss what do we mean by a leverage point. Okay, so leverage point usually means that this point has unusual x coordinate in comparison to other points in the data set. Okay, so let's say this is my x value and this is the y value. The first step was to plot a scatter plot. Okay, so let's say our data set is such that the scatter plot ranges in this direction. Now suddenly if I have too high an x somewhere here, then this is usually, because my x's are centered around, let's say 1 to 2. Now if I suddenly have x as 100, okay, then this one is my leverage point, because it has unusual x value with respect to other data points in the data set. Okay, so this is actually a leverage point. Now a leverage point, okay, this is what we mean by a leverage point. Now next we learn about influential point. Influential observation. Now influential observation is one observation which alters the regression line. Okay, it could have unusual, with how does it alter? Unusual x and y values. Okay, so let's say this is the thing. In the previous one, in this particular example, if the regression line is this, let's say, then we can say that this one is not, in this particular case, this point is not influential. Because why? Because it is not distorting the original regression. Because it is not distorting the original regression. Alright, but here if we have an influential observation, it is bound to alter the regression line. Okay, so let's say we had a scatter plot like this. Okay, and the regression line in this case would be this, let's say. Alright, but now if we have something like this, okay, and because of this variable, this point which has unusual So let's say this somewhere here, which has okay, so this is unusual x and unusual y. Okay, so inclusion of this point, if it distorts the original regression to something like this, then this one is actually my influential point. Okay, now to comment whether a leverage point can be an influential point or not, we need the value of the y coordinate at that point as well. Okay, so if it has both unusual x and y, so much so that it is altering the, or it is totally changing the regression line, then we can say that this is an influential point. Otherwise we don't say that this is an influential point. Okay, I hope this is clear to you. Alright, then moving on. Okay, so we learned about leverage point and an influential observation. What else did we learn about? We learned about a very important thing which is known as the hat matrix. Okay, now which one is actually my hat matrix? So yeah, so what do we know about the hat matrix? Okay, so hat matrix is derived as follows. So if we have this model, let's say y equal to x beta plus epsilon, then and the assumptions hold true, which is what? Expectation of epsilon I equal to 0, variance of epsilon equal to sigma square I, then we have beta hat OLS as x transpose x inverse x transpose y. OLS is ordinary least squares, whatever we have learned. Okay, now then y hat becomes x into beta hat, which is x transpose x inverse x transpose y. Now this can be written as hy. Okay, where h is this thing, x transpose x inverse x transpose, and this actually is my hat matrix. Okay, so there are a few properties of this hat matrix that we have learned. So as you can see from here, h is symmetric. Okay, so h is what? X into x transpose x inverse x transpose. So h transpose is x into x transpose x inverse x transpose whole thing transpose. So we know that A B transpose equal to B transpose A transpose. So this then comes to front. So this will have be what? This is, so yeah, so this will become x transpose will become x, then x transpose x inverse will remain x transpose x inverse, and then x transpose will, this x will become x transpose. so which is H. Alright, so H prime equal to H means that this is symmetric. Okay, and another property also we have of this hat matrix is idempotent. So what do we mean by idempotent? It means that H square equal to H. So X into X transpose X inverse X transpose into again X into X transpose X inverse X transpose. So then this becomes X transpose X inverse X transpose X, and then again X transpose X inverse X transpose. So one of this cancels with this. So we have which is nothing but H. Alright, so this is actually an idempotent matrix, that is the hat matrix. Alright, and next what have we learnt? We have learnt how to find out the residuals. So residuals means what? Residuals is this thing. Residuals is y minus y hat. So this is y minus hy. So this is y into 1 minus, or rather I minus h. Okay. So then if we write it down properly, if we decompose y into its linear model format, then what do we have? Sorry, this should be written as I minus h into y. Just be careful because this is matrix multiplication, we should not change the order. So this then becomes I minus h x beta plus epsilon. Okay, so then this becomes x beta minus hx beta plus I minus h into epsilon. Okay, so h into x becomes what? So we'll write down x, this is x beta minus x into x transpose x inverse x transpose into x beta plus I minus h epsilon. So then this one and this one cancels, x beta becomes 0. So residuals broadly can be written as I minus hat into epsilon. Okay, so if residuals can be written in this manner, then what becomes the variance of the residuals? So variance of the residuals then becomes I minus h, variance of I minus h into epsilon. Okay, so then this becomes I minus h, variance of epsilon into I minus h transpose. So then this is what? This is I minus h into sigma square I into I minus h. Okay, so then this is sigma square into I minus h square. Alright, now since h is idempotent, I minus h is also idempotent, and therefore sigma square I minus h whole square will also be equal to sigma square I minus h. Okay, so we clearly see that if we draw the variance covariance matrix of this vector of residuals, then we see that the diagonals, from here what we infer is that variance of EI will be equal to sigma square into 1 minus HII. So then, depending on whether the x observations, whether the whether the x observations, how they fare, that will determine variance of EI. It no longer remains constant. It is dependent on HII, which in turn is dependent on my XI values. Okay, so then this from here we can say that the errors, error variance, variance of epsilon I, even though that is constant, the residual variance is not constant. That is, variance of EI is not equal to some k. Okay, it varies depending on the value of xi. Alright. So from here another observation is that since this is I minus h, we find that the residuals are correlated. Okay, errors usually 1 not. Okay, but the residuals that we have, they are correlated because covariance of EI, EJ, from here variance of E equal to I minus HH. So I is an identity matrix with diagonals as 1 and off diagonals as 0. So covariance between EI and EJ will be actually 0 minus HIJ. Okay, so then this will be H minus HIJ and not equal to 0 usually. So then we can conclude that the residuals are correlated whereas the errors were not. Alright. Now another thing is, what does HII measure? So we have to note that HII is capped between 0 and 1. Okay, and it measures the distance of xi from the center of x coordinates. So then how do we interpret this? The HII closer to 1 means more likely the point is a leverage point, because this is purely based on the xi observations. But if HII is closer to 0, then less likely of it to be a leverage point. Alright, fine. After this, what else did we learn about? So we learned about the hat matrix, we learned about the properties, we learned about the significance of the diagonals and range of HII. The next thing that we are going to learn about is standardized, studentized and press residuals. Okay, so let's just find out. Okay, so standardized residuals is nothing but, usually denoted with di, is actually ei by root over ms residual. Okay, so standardized uh, uh, by how much? So variance of ei is actually equal to sigma square into 1 minus hii. Okay, so if this is close to 0, that is that there is no influential observation, then we can write that variance of ei is approximately equal to sigma square. Okay, if we just ignore this hii term, and sigma square hat is actually nothing but the ms residual from the model that we have seen in the previous classes. Okay, wherever we have to estimate sigma square, we do that with ms residuals. So then we can have this sigma square hat as ms residual, and we just take the residuals and then standardize it with the assumption that variance of ei is approximately equal to sigma square and not that far away from the x's are not that far away from each of the centers. So okay, even though keeping this thing in mind, we have this standardized residuals designed in this way, where this di is ei by root over ms residual. But as you can see and appreciate now, this is not the correct thing to do. So then what do? In order to do the correct thing, we take studentized residuals. Okay, so here this is denoted by ri, which is nothing but ei by root over ms residual into 1 minus hii. Okay, so here we standardize it by the correct variance, because variance of ei is actually sigma square 1 minus hii, and we estimate sigma square by ms residual of the model. Okay, so this is how the studentized residual looks like. Okay, so if let's say we have this, that the ith observation is leverage, let's say. Okay, in some cases influential. Okay, if that holds, then what happens? This implies that hii will be close to 1. Okay, so then this value, if this is close to 1, this will be close to 0. So this ri will be, so what will happen is that this entire quantity will increase, rather than if we have hii equal to 0 or hii equal to 1, sorry, hii equal to 0, when it's not a influential, or it's not a leverage point, then this one will be smaller. Okay, but if it is a leverage point, then this one is higher. Okay, so if ith observation is actually leverage, we will have ri greater than or equal to, not equal to, it will be strictly greater than, because we will have non-zero values in hii. This will be greater than di. Alright. Fine. So After learning about these two kinds of residuals, standardized and studentized residuals, we also learned about a third kind of residuals, which is known as press residuals. Now, calculation of press residuals can be a little tedious and tiresome, because what happens in press is that we fit models excluding the ith observation. So that involves a lot of model fitting and then getting the subsequent parameters. So this is how we find out the press residuals. Alright, now how does press work? Press residual is denoted by EI, which is actually observed yi minus yi predicted without the ith observation. Okay, so let's say if I go here to this inflated example, originally let's say this is the disturbing point that I have in mind. Okay, so this is, let's say, my influential point. Alright, so if this is my influential point, initially the original regression was supposed to be this thing. It was supposed to be this thing. Because of the presence of this one, the regression got tilted towards this thing. Alright, so then what happens? This is actually my xi yi. Okay, because of the presence of this one, keeping the ith observation intact, if this is the xi yi, then somewhere here along this line, in this blue position, we'll have xi yi hat. Okay, and if we remove this ith observation, then the regression line is not distorted. In that case, we have a prediction here somewhere. Okay, and that is actually xi yi hat. That is, we remove the ith observation from the data set and then get the y predicted. Okay, so then yi minus y predicted in that case is greater. So if ith observation is influential, then what do we have? We have that EI to be less than EI. Alright, because EI is only this much. It is designed and EI is fitted in such a way such that the observation, the vertical distance between this point and the fitted line remains smaller. Okay, but if this point is actually influencing my regression line and pulling it or distorting it in any manner, then if I remove this, then the difference between the fitted value and the observed value will become way larger. So this is also another way that we can find out whether an observation is influential or not, by comparing their normal residuals with their press residuals. Okay, and we can show that EI, where is the cursor? We can show that EI can be written as EI by 1 minus HII. Okay, so this also shows that this is actually greater than EI. Alright, so after learning about the different types of residuals, we also learned about some visualization techniques to determine whether the underlying assumptions while fitting the model they hold or not. Okay, so we learned about some of the plots. The first plot that we learned was residual plot. Okay, so how does a residual plot look like? So what do we plot? We plot EI, that is the normal residual, versus fitted values. So after fitting a linear regression of sorts, we get EI values and we get Y hat values. So we'll plot Y hat along x-axis and EI along y-axis. Okay, and if we see something close to 0, let's say this is the EI equal to 0 line and points randomly scattered around 0. This is something ideal. We'll be very happy if we see something of this sort. This means that EIs and YIs are uncorrelated and they have been fitted properly. Okay, so expected ideal is no pattern, mindful, no pattern, randomly scattered points on EI versus Y hat graph. Okay, and in randomly scattered about 0, randomly scattered points about 0. Which variable 0 among about EI equal to 0. Okay, so if we have something like this, that we find number 1, random scatter about 0 and random scatter implying no pattern. There shouldn't be any increase decrease visible. So if this is the case, then we can say that okay, our results support the underlying model assumptions. Alright, so this was a residual plot that we learned. Now, in case if we don't get such a clear graph, then what does that indicate? So if there is no pattern between Y hat and EI, it shows that EI and Y hat are actually uncorrelated. So this one actually depicts EI and y hat as uncorrelated. This is expected because we want our predictions to be robust and we do not want it to be correlated with the error or estimate or error that we are making. Okay, so this was about the residual plot. Now what I want to highlight is that sometimes you can observe patterns like this where EI is this, y hat is this is the EI equal to 0 line, but you find something like this funnel shaped things, something like this pattern. So what does this mean? This means that as y hat increases, EI decreases. Or if we have a scenario like this, y hat EI, this is the y equal to 0 line, and then if we have something like this, sorry, this is as EI increase, this is not EI, this shows that as y hat increases, variance of EI is increasing because the scatter or range of EI is increasing. Alright, and we can have something like this also. So here we have a lot of points, and then as y hat decreases, something like this. So this implicates what? It implicates that as y hat increases, variance of EI is decreasing. Both of these are violations of the underlying assumptions of OLS. Okay, so ideally we would want something which has no scatter and no pattern with respect to the fitted values. Okay, so ideally what do we want? As I was saying, ideally we want something like this, that all the points are restricted within they fall within this rectangular region, which should be an acceptable limit. Okay, so if something like this happens, then we can say that the model doesn't have any obvious defects. Alright, and another problem or another pattern that you could also see is this one. You could also see some non-linear pattern. So if I have y hat here and EI here, this is the y equal to 0 line. If we have something like this, a parabola, let's say, so this one is indicative of a non-linear form. Okay, so this one is also not desirable. Okay, so after this we also learn about something else, which is the plot of residuals on regressors. Okay, so we also learned about this plot of residuals on regressors. Okay, so what does this show? This actually um, depicts relationship between y and predictor xi. Okay, so in case we have something like this, where we have ei and xj, and this is equal to 0 line, we have something like this, random scatter about 0, then we are good to go. Okay, but if we have something like this, as we previously saw, something like this or something like this about the equal to 0 line, this is xj, this is ei, okay, or some sort of a non-linear relationship, let's say something like this. So these are situations which we'll be able to find out the relationship based on these graphs. Okay, but then this one has one issue. This is only going to show a relationship between xj and y only, but not the relationship when there are other regressors apart, when there are other regressors apart from xj. So this one is mostly useful when we have a simple linear regression, because in that case we just have one predictor variable. But if we have multiple predictors, which is true in the case of multiple linear regression, then this method comes with this its own challenge, that this relationship will not depict the true relationship between xj and y in the presence of other regressors. Alright, so it's best to use this method while doing a simple linear regression. For a multiple linear regression, we should go ahead with plotting ei against the fitted values. Okay, so we learned this as well, and what else did we learn? Apart from this, we also learned about partial residual plots.